pair view. The next thing we're going to show is, I know you went through some of these examples this morning. We're going to go through a Green's function example in 3D Hex 8. I won't go through the mesh generation because I know you already did that. This particular one runs differently from the others, and that's because we have to switch the problem type to Green's functions. So that's the main difference. So I know you've already seen the PyLith app.config for 3D Hex 8. So let's look at the Green's functions.config. So here we again have our general description. You'll notice that the problem type is now Green's functions rather than PyLith app. Here's how we run the example. Again, we need a fault ID. Here we've just used fault ID of 10. We again are using fault cohesive impulses. So rather than say fault cohesive kinetic, in this case, we're going to impose both left lateral and reverse slip for our impulses. So we'll have two sets of, we'll have double the number of Green's functions since we have both left lateral and reverse slip. So here we're telling it we're going to use both of them. We're again going to have an amplitude file, which is again called impulse amplitude.spatialdb. We're going to use nearest neighbor interpolation. Let's look at this file. So for this file, we have just a single value is slip. We're going to specify the slip in meters. We have we're going to give it 10 locations because we're going to maybe it would be handy to look at this. No, I'll look at it after we generate it so we can see what we did. But essentially, we're providing slip between -2 and +2 in the x direction. Let's see. Yeah, and between, let's see, 0. I have to look at, let's see. Our plane is, I have to remember what this mesh looks like. We're specifying it on the interior nodes on here. I'm going to look at what our mesh looks like. Let's just look at our mesh. Right, where is our mesh? Oh. So we have, let's just look at the fault. Okay, so the fault lies along x equals 0. So where we're providing slip is between yep, between y equals -2 and +2. That's what it is. Yep, sorry, I was reading that wrong. And then between x is -3 and x equals 0. So we have that fault and then, or that file, and then we have the one that's specific to step 21. This is again how we're going to run the problem. Total time of 0 seconds, dt of 1 year, which doesn't really matter for static elastic problem. Our boundary conditions are Oh yeah, yeah. So just on the positive and negative x boundaries and then at the bottom. So we'll have boundary conditions here, here, and then on the bottom of the mesh. We have a interface array that is just one component, which is fault. Then we're going to output the solution for both the domain and points. So this is our output array. And so we have to tell it what points means. That means that we're going to output output solution points. That's our type of output. And we'll give it the set of points where we're going to output the solution. We have our boundary conditions. So our x positive, we're fixing both x and y on that boundary. X negative, same thing. And then on the bottom boundary, we're just fixing the z component of displacement. For our faults, we give our ID number of 10. The label is equal to fault. You'll notice that this fault goes all the way through our mesh, so we don't have to give a fault edge. If you look here, you can see it goes from the top all the way down through the bottom. So we don't have a buried edge of the fault. We have to give it the quadrature information. So these are hexahedral elements, which is a Fiat-Lagrange element, and the fault cell dimension is equal to 2, since it's a surface. And then we just give it the output information. So for domain, we're going to have HDF5 output. We give it the output, the name of the output file for the domain. For the points, we've already told it that it's output solution points. And now here we're telling it we want HDF5 output. Here's what we want the output file name to be. And then here are the points where we want to produce the displacements computed from our impulses. And then for this points file, we have to give it the spatial dimension, which is 3. We're going to give our coordinates in meters. And then that's all the information for that. Then we just have our fault output, HDF5 output, file name. We want it to output the area and the impulse amplitude for our information. And then we're not going to output any cell information for this problem. That would be the stresses and strains, and the and then for the info, that would be like density, shear modulus. And then same way for upper crust and lower crust, we're not going to output any. Okay, if we run this in parallel, we can also output our mesh partition information. I suppose we could do that for this, just for fun. Let's first look at files that we're using. So we have Green's functions points.txt. So these are the points where we're going to output the solution. And this is 3D, and as you recall, we said we'll do the coordinates in meters. So first we give it the station's name, then X, Y, and Z coordinates. Here, the Z is again slightly below the ground surface, so we don't end up with any points that PyLith thinks are outside of the mesh. Let's see, then what else? I think we've covered everything because we already looked at the impulse amplitude. So if we look at, here's how we run our problem. Just for fun, we'll run on 2 nodes. And then Okay, so now we've generated our Greens function. The output will be in the output directory. That's all these step 21 files. So we'll look at that. Get rid of the mesh. Let's look at the fault and the points. So, okay. So here we are with our fault, and then the points at which we've computed the solution. So the faults, there we go. And let's show what we've done. Now, in this case, on the fault, we haven't imposed just one component of slip. We've imposed slip in both the left lateral and reverse slip direction, but you'll see they're separated from each other. So this first one, we've just imposed left lateral slip. The next impulse, okay, no, I always forget which way they're ordered. So if we were to go to let's go to step 20. Then let's go one more. Oh, well, maybe they're not ordered how I think. Go back. Did I not do? I have it wrong.
It'll be X and Y, Charles.
What's that? Will be X and Y. There's X. Oh, wait a minute. It's not. Maybe it's playing too fast. Oh, I know why. Is it? It's because there. It's because one was negative. It wasn't showing up. So if we show Y, there we go. So it is every other one. Like that. So that's our imposed slip. We can, let's just look at the slip magnitude. And then let's look at, in this case, we can just plot the vectors directly since we have a displacement vector. Let's try this again. See what that does. Oops, too big. Okay. So now again, you can see what these on the fault is your implied impulse, and then these vectors are showing the surface response due to that impulse. So this is a left lateral impulse, and then we can just kind of go through and see what they do. That's a reverse impulse, and they're alternating back and forth here. So you can go through and see what all the different so this would be your Green's functions generated for 3D. And if you were motivated, what you could do is set up a similar inversion like we did for the 2D example. That might be a good exercise for people. Anyway, I think that's pretty much covered the Green's functions. So do we have questions about that? I can go back to the original.
Yeah, so we have a question.
Okay.
Question is, can we use the same procedure you described for multiple fractures? For example, we have multiple opening fractures under the ground, and by using surface deformation to find opening distributions along those multiple fractures.
Yes, yes, you can. You just have to make sure that you keep track of your greens functions, because typically in a case like that, you would generate one set of greens functions per fault, and then in your code to perform the inversions, you would open up all of the impulses and responses for those different. I would think that it would be easier to keep track of things if you do it that way. I'm actually doing that right now for multiple faults in New Zealand, so it's yes, you can definitely do that. The other thing is, if you're restricting yourself to linear elastic behavior, you can actually have a completely different mesh for each of the faults, if that makes it easier, as long as you're interpolating the results to the same set of points, because you can linearly superimpose your solutions. Okay.
Then get an output displacement vector along the line of sight.
That you would have to do that in post-processing. This would be like you would have for, say, INSAR or something, I'm guessing, or maybe LiDAR. In that case, you would have to, you could do it in ParaView, but I would think you'd be better off doing something with a little bit of Python code to just dot the displacement components onto your look vector. Why is this bouncing up and down? Let's see. Did that answer that question?
I think that answered that question. We have another question. Can we tell about source fault type by observing slip? I mean, if we invert displacement in XY coordinates.
Can we tell about source fault type?
So I believe that means slip direction on a fault surface, if we have vertical and horizontal displacement.
Well, that's a more general question. Usually, I mean, to do the kind of thing that we're doing here, you need to know something about the fault geometry. Preferably, you would actually know the fault geometry. As far as slip direction, you don't have to constrain that, although usually you want to constrain it just a little bit or you'll end up with a really rough and probably nonsensical slip distribution. Yeah, to do the type of inversion that we're talking, or the type of problem that we're talking about here, you want to know something about your source fault before you start. And you can infer something. I mean, if you see an up-thrown side and a down-thrown side and you don't see much along strike deformation, you can assume that you have a dip slip fault, but I don't know if that's the question they're asking or not.
Another question, extracting elastic medium parameters through surface displacements using PyLith.
We can't do that yet. That's would be the adjoint problem, which we have not yet implemented. The only way you could do it at present is with numerous inversions. For instance, if you thought you had two layers in your problem that might have different properties, or maybe that you had two materials, one on either side of the fault, you could try inversions where you buried those properties, but that's essentially using forward models to solve an inverse problem. We don't have a way of inverting for properties at present.
Charles, I'm going to switch to the Q&A so you can see the questions in the chat.
Let me see.